Hello, everyone. Welcome to Research for Starter, Class 1 Fundamental Workflow. Today, we are now just learning science. We are learning how to think like a researcher. Research is not about memorizing answers. It is about asking questions that do not yet have clear answers. In this class, we will build the foundation of research thinking, from curiosity to hypothesis, from idea to structure. Let's begin with a simple question. What is study? I'll give you 1 minute. Study means learning knowledge that is already known. The answers already exist. You're learning, understanding, and remembering them. Now, what is research? I'll give you 1 minute. Research means asking new questions and finding new knowledge. The answer is not fully known yet. You investigate it. So the difference is simple. In study, the answer already exists. In research, the answer does not yet exist, or it is not fully understood. That is very powerful difference. Now, let's express this difference more clearly. In study, knowledge me equal knowledge known. You are trying to make your knowledge equal to what is already known. But in research, knowledge new equal knowledge known plus delta knowledge. That delta knowledge represents new knowledge. And importantly, no delta knowledge must be greater than zero. Research always adds something, even if it is small. Now let's compare them in three ways. First, the question. In study, the answer is already known. In research, the answer is not yet known. Second, the process. Study follows these paths: learn, understand, and remember. But research follows a different pathway. Question, collect data, and explain. Third, how success is measured. In study, success is accuracy. Did you get the correct answer? In research, success is measured by evidence, clarity, and repeatability. Can other people understand your logic? Can they repeat your method? That is what makes research scientific. Good research starts with a clear, measurable, and testable question. And most research begins with curiosity. Why, how, and what if? Now we move to a critical step in research, how to identify a research topic. A research topic does not appear randomly. It usually emerges from one of three sources: curiosity, observation, or existing knowledge. We can categorize topic development into two major approaches. First, the bottom-up approach. This approach begins with personal interests, daily observation, or simple question. It is driven by curiosity and real-world experience. Second, the top-down approach. This approach begins with existing scientific literature, identified gaps in research, or unresolved problems in a field. In academic research, both approaches are valid. However, strong research often integrates both. We can summarize this idea mathematically. Topic equal curiosity plus background knowledge. Curiosity alone is not enough. Background knowledge alone is not enough too. A meaningful research topic connects what you observe with what science already knows. Now, let us critically compare these two approaches. First, the bottom-up approach. Its advantages are clear. It creates high personal motivation. It encourages creativity. It often produces original ideas. And it provides an easy starting point. However, it also has limitation. It may lack scientific depth. The feasibility of the project may be unclear, and sometimes it overlaps with existing research without realizing it. Now, consider the top-down approach. Its strengths are different. It is grounded in existing literature. It has clear scientific context, and it makes hypothesis construction easier, and it usually aligns well with academic standards. But it also has limitations. It may feel less original. It requires significant background reading, and sometimes it limits creativity. Therefore, strong research rarely relies on only one method. Research often combines curiosity from bottom-up thinking with structure and evidence from top-down reasoning. Let's now examine a real-world example of bottom-up topic development. We begin with observation. Recent reports shows increasing measles outbreak in the United States. This is not just news, it is scientific and public health signal. From this observation, we move to a question. Observation, measles cases are increasing. Question, what is measles spreading again? And from that question, a research topic emerges. Factors affecting measles transmission. Notice the structure here, observation, question, and research topic. This is how bottom-up research thinking works. You begin with something you observe in reality. You transform it into scientific question, and then you refine it into researchable topic. This transition from curiosity to structured inquiry is what transforms an idea into research. At this stage, we must move from a broad theme to a focused research topic. Measles outbreak is not yet a research topic. It is a general theme. Academic research requires specificity. A broad topic lacks clarity, measurable variables, and methodological direction. Therefore, we narrow it. For example, instead of measles outbreak, we might examine the relationship between vaccination rate and infection spread, the role of public awareness in disease prevention, early detection using medical screening tools. Notice the transformation. We move from general social issue to a question that can be measured, tested, and analyzed. This process is called operationalization. A research topic must allow defined variables, measurable outcomes, and feasible methodology. Without narrowing, a topic remains an idea, not a research project. Once a topic is narrowed, the next step is to identify a research gap. A research gap refers to an area that has not been fully explored, improved, or optimized in existing knowledge. Let us analyze the measles example more critically. Outbreak control depends heavily on early detection and rapid intervention. However, measles progresses through several stages. Incubation period, no visible symptoms. Prodromal stage, early warning sign appears. Rash stage, visible clinical diagnosis becomes easier. Now, consider this carefully. Complex spots appear in a prodromal phase before the rash develops, yet these early signs are often overlooked. This creates a gap. The disease becomes contagious before a visible rash diagnosis, but early indicators are underutilized. Now we connect this gap to available technology. Smartphones are widely accessible. AI-based image recognition is rapidly advancing. This suggests a potential research direction. Can smartphone-based AI detect early oral symptoms to improve outbreak control? Observe the full logical chain: observation, problem, gap, possible solution, and research topic. This structured reasoning is what transforms a topic into a novel research proposal. Now, we must evaluate the strengths of this topic. Not every idea becomes good research. A strong research topic satisfies several criteria. First, it addresses a real-world problem. Measles outbreaks are not theoretical concerns. They have direct public health consequences. Second, it has measurable outcomes. We can quantify detection accuracy, sensitivity, specificity, and compare performance between models. Without measurable outcomes, a study cannot produce scientific evidence. Third, it connects science, technology, and social impact. This topic integrates biology and clinical symptom recognition, artificial intelligence, and public health application. This interdisciplinary connection strengthens the academic value of the project. In summary, a good topic is not just interesting. It is relevant, measurable, and impactful. Now, it is your turn. What is the biggest scientific issue where you live? And what topic genuinely interests you? Because research must begin with ownership. I'll give you 1 minute and fill in the blank. Okay, let's move on. Now we enter a very important stage of research, the theoretical background. Every research topic already has a background. No research begins in isolation. Before starting, we must understand existing knowledge. Let me ask you, why do we already know about this topic? Think about missiles. What facts are already established? What has been scientifically confirmed? Take 1 minute and write down at least 3 things you already know. Now, let us organize the existing knowledge scientifically. First, what is measles? Measles is highly contagious viral disease caused by the measles virus. It is transmitted through airborne particles via coughing, sneezing, or close contact. The incubation period is approximately 7 to 14 days. Now, let us examine the major symptoms. High fever, cough, coryza, meaning runny nose. Conjunctivitis, inflammation of the eyes, and characteristics spreading rash. However, before the rash appears, there is an important early clinical sign, Koplik spots. These are tiny white or bluish spots with a red halo found inside the cheeks. They appear 1 to 2 days before the rash and are considered pathogenic for measles, meaning they are highly specific to the disease. But here is a problem. They are often difficult for non-doctors to recognize, and this difficulty where our research opportunity begins. Now that we understand the background, we must ask a critical question. What is the research gap? A research gap refers to something that has not been fully explored. improved, or optimized in existing studies. Good research does not simply repeat what is known, it identifies what is missing. There are several strategies to create differentiation. First, improve accessibility. Can we make diagnosis easier for non-specialists? Second, increase detection accuracy. Can we improve sensitivity or reduce false negatives? Third, reduce cost. Can we replace expensive equipment with widely available tools? Fourth, improve usability. Can we design a system that ordinary users can operate? Now, I want you to think, what improvements does your research provide? If your project cannot clearly state its improvement, then it does not yet have novelty. Novelty is not about being completely new. It is about improving, refining, or applying knowledge in a better way. At this stage, we must discuss literature review. Every academic research project begins with understanding existing scientific knowledge. The purpose of a literature review is not just reading papers. It serves four critical functions. First, to understand what is already known. Second, to identify research gaps. Third, to avoid duplication of prior work. Fourth, to justify novelty. Literature review forms the intellectual foundation of research. Now let us address the role of AI. Generative AI is not a source of scientific evidence. It does not replace peer-reviewed literature. Instead, it functions as a research assistant, an idea organizer, a keyword generator. The key principle is this: AI helps thinking. Paper provides evidence. If you remember only one sentence from this slide, remember that one. Now we move from theory to execution. Before conducting a literature search, you must define the scope of your research clearly. And undefined scope leads to unfocused searching and superficial understanding. Let us break this into structured components. First, disease or condition. You must specify exactly you are studying. Not infectious disease, but which disease. Not viral infection, but which virus. Second, target population. Who is your study focused on? Children, adults, unvaccinated individuals? A clearly defined population increases scientific precision. Third, methodology. What tools or techniques will you use? Image analysis, survey, experimental measurement. Methodology determines the type of literature you must review. Fourth, application field. Is your research clinical, public health oriented, technological development? Now take 2 minutes, fill in each category for your own research idea. If you cannot define these 4 elements clearly, your topic is still too broad. Now that the scope is defined, we generated academic keywords. Keywords are not random words, they are strategic tools. We categorize them into three groups. Core concept keywords. These represent the scientific essence of your topic. Method-based keywords. These reflect how the study is conducted. Application-oriented keywords. This indicates practical context and impact. If your keywords are poorly constructed, your literature review will miss critical paper. Think carefully. Which word would researchers in your field use? I'll give you 2 minutes. Now, let us apply the structured framework to our measles example. Step 1, define research scope. Disease or condition. Measles infection with focus on early order symptoms, especially complex spot. Notice how specific this is. We are not studying infectious disease. We are not even studying measles broadly. We are focusing on early order symptoms. Target population, individual at risk of measles exposure, especially children and unvaccinated population. A defined population increases scientific clarity. Methodology, smartphone-based image capture combined with AI image recognition for early symptom detection. This tells us immediately what types of literature we must review. Computer vision, mobile health, and infectious disease diagnosis. Application field, public health screening, early disease detection, digital health monitoring. Now, step 2, generate academic keywords. Core concept keywords, measles, complex spots, early diagnosis, infectious disease detection, symptom recognition. Method-based keywords, smartphone imaging, AI image recognition, machine learning, diagnosis, computer vision, mobile health. Application-oriented keywords, public health surveillance, outbreak prevention, telemedicine screening, digital health diagnostics. Notice something important. We are not guessing keywords. We are constructing them systemically from our defined scope. That is how professional researchers search literature. Now, we move to actual literature search. Generating keywords is preparation, searching and evaluating papers in execution. Step 3, literature search. You should use academic databases such as Google Scholar, PubMed, and prioritize review article first. What review articles? Because review papers summarize existing knowledge, identify trends, and highlight research gaps efficiently. After reading at least one review paper, you should select at least one original research article. Now, comes the most important part, critical evaluation. Do not just read paper, analyze them. Ask, what problem did this study address? What method was used? What were the limitations? What remains unresolved? For example, our topic is early detection of missiles through smartphone-based recognition of complex spots. When using AI tools such as ChatGPT or Gemini, use them only to define scope more clearly, generate alternative keywords, refine conceptual structure. But the evidence must come from peer-reviewed literature. Your final task is this. Explain how prior studies related to your research idea. If you cannot articulate that connection, you have not completed your literature review. Now, let us examine what happens when we search missiles and AI in academic databases. We quickly discover that research already exists. In the highlighted paper, the one in the red box, we see a study that applies artificial intelligence to detect missile-related symptoms. This is important because it tells us two things. First, our idea is not isolated. The scientific community is already exploring AI-based missile detection. Second, we must now differentiate our approach. Research does not begin from zero. It begins from existing work. The question is not, has this ever been studied? The question is, how is our approach different? If previous studies focus on skin rash detection, what stage of missiles are they analyzing? The rash stage. Now think critically. Does rash detection represent the earliest possible diagnosis? No. That is where our novelty emerges. Our research shifts the focus from rash stage detection to prodromal stage detection, especially complex spot. We are now repeating prior work. We are extending it. That is the essence of academic research. Now, let us clearly articulate the distinction. Existing studies primarily focus on skin rash-based detection. Rash detection occurs during the rash stage of missiles, but consider the timeline of disease progression. The rash stage appears after the prodromal phase. Complex spots appear earlier in the prodromal phase before the rash develops. This temporal difference is critical. If detection occurs at the rash stage, transmission may already be ongoing. However, if detection occurs at the complex spot stage, intervention can happen earlier. Earlier detection leads to faster isolation. Faster isolation reduces transmission risk. Therefore, our novelty lies not in applying AI to missiles, but in shifting the diagnostic window to earlier stage of disease progression. The shift creates potential impact in outbreak control and public health response. This is how we justify our research contribution. Now that we have explored how to use AI in research, we must discuss how to use it responsibly. AI is a powerful research assistant, but it is not replacement of human thinking. Generative AI can help us organize ideas, generate keywords, summarize background information. However, AI-generated content may contain errors, biases, or outdated information. Therefore, early piece of information must be verified with reliable scientific sources. Critical thinking must remain human-driven. Let me emphasize this clearly. AI supports reasoning. It does not replace reasoning. If you allow AI to think for you, you are no longer conducting research. You are delegating it. responsible research requires ownership of intellectual work. Responsible AI use is closely connected to academic integrity. Academic integrity means honesty, transparency, and intellectual responsibility in research. One major concern is plagiarism. Copying AI-generated text without understanding it is still plagiarism. Even if AI produces it, research requires comprehension. If you cannot explain a sentence in your own words, you should not include it in your work. Another key principle is transparency. If AI assisted in generating idea or organizing structure, that assistance should be acknowledged appropriately. Clear distinction must exist between your original contribution and AI-supported content. Scientific credibility depends on trust, and trust depends on transparency. We now broaden the discussion beyond AI. Ethics in scientific research is not optional, it is foundational. All research must follow ethical principles. There are three core pillars. First, honesty. Data must be reported truthfully, no fabrication, no select reporting, no manipulation. Second, reproducibility. Your method must be described clearly so that other researchers can repeat your study. Science advances through replication. Third, respect for subjects. This is especially critical in medical research. If human participants are involved, their privacy, consent, and safety must be protected. Finally, responsible innovation. Technology should benefit society and minimize harm. Scientific progress without ethical consideration can cause serious consequences. Remember this sentence: good science is not only about result, it is about responsibility. Now, we move into research design. A hypothesis is a testable statement about the relationship between variables. It is not a guess, it is a structured prediction. A strong hypothesis must satisfy three conditions. First, it must be clear. Anyone reading it should understand what is being compared or tested. Second, it must be testable. There must be method to collect data. They can confirm or reject the statement. Third, it must be measurable. The variables involved must be quantifiable or at least observable. Let us examine our missiles example. A simple hypothesis might be smartphone-based recognition of complex spots can improve early missiles detection. However, we can make it more precise. Combining complex spot recognition with systemic symptoms such as fever, cough, coryza, and conjunctivitis improve early missiles detection accuracy compared with using complex spot alone. Notice the difference. The second hypothesis defines what is being compared, which variables are involved, and what outcome will be measured. This is what makes it scientifically testable. In this stage, we must clarify a critical distinction. Correlation is not the same as causation. Correlation means two variables change together, but it does not mean one variable caused the other. For example, lower vaccination rate correlate with higher measles case. This means they are associated. However, causation means one variable directly influences another. Reduced vaccination cause increased measles transmission. That is a causal statement. Now think carefully. How do we determine causation? Causation requires stronger evidence. Controlled variables, temporal precedence, mechanistic explanation. Mechanistic explanation. Many studies shows correlation. Fewer studies can demonstrate causation. Understanding this distinction protects us from making exaggerated claims. Now we formally define variables. The slide begins with key sentence. A hypothesis is a testable statement about relationship between variables. That means without variables, there is no hypothesis. So, what are variables? A variable is anything can change or take different values. First, the independent variable, IV. This is variable you change or the condition you test. It represents the cause or input in your design. Second, the dependent variable, DV. This is the outcome you measure. It represents the effect or result. We can summarize this relationship as independent variable to dependent variable. The independent variables influences the dependent variable. Now we move to control variables. Control variables are factors that must remain constant to ensure fair testing. What do control variables matter? Because without them, results may be misleading. Even if your independent variable changes, your outcome may actually be affected by something else. That leads us to an important concept, outcome equal independent variables plus controls. The outcome is influenced not only by the independent variable, but also by controlled conditions. If controls are unstable, the relationship between independent variable and dependent variable becomes unclear. Finally, I introduce confounding variable. A confounding variable is a hidden factor that unintentionally influences the outcome. It creates first relationship. If not identified, it can make correlation appear like causation. Understanding variables is not optional. It is the foundation of valid scientific research. Now, let us apply everything we discussed to our results example. Here is our hypothesis. Combining complex spot recognition with systemic symptoms such as fever, cough, coryza improves early measles detection accuracy compared with using coupling spot alone. Notice how structured this statement is. It clearly compares two diagnostic approaches. Approach 1, complex spot recognition only. Approach 2, complex spot recognition plus systemic symptoms. This comparison is measurable. Our dependent variable is detection accuracy. Now, why does this hypothesis work? First, it defines measurable variables. We know exactly what changes and what we measure. Second, it compares it to detection approaches. Comparison is essential in scientific testing. Without comparison, there is no evaluation. Third, it allows quantitative testing. We can calculate accuracy, sensitivity, specificity, and statistically compare the results. Now, look at the figure. This diagram shows multimodal early measles detection. Each symptoms provide diagnostic information. When information is integrated, diagnostic certainty increases. And this is the key logical sentence. If multiple early symptoms are integrated, then early detection accuracy increases because more diagnostic information is used. This is not speculation. It is information theory applied to diagnosis. More independent signals reduce uncertainty. That is the scientific logic behind our hypothesis. Now, let us apply correlation and causation directly to our measles example. First, correlation. Fever and coupled spots often appear before the measles rash that occur together. But do they cause each other? No. They correlate, but they do not cause one another. Now, consider causation. The measles virus infection causes both fever and coupled spot. This is the true causal relationship. So remember this key sentence. Symptoms correlate, but the virus causes them. This distinction is critical in research. When building an AI detection system, we are not claiming that fever causes coupled spot. We are using correlated signal to improve prediction accuracy. Now, let us define our variable clearly. Independent variable, the type of detection approaches used. Option 1, coupled spot only detection. Option 2, multi-symptom detection. Coupled spot plus fever plus 3 C's. Dependent variables, early detection accuracy. And how do we measure that? Sensitivity, specificity, overall accuracy. Notice what we are testing. We are testing whether changing the diagnostic strategy changes detection performance. That is a clean experimental structure. Now we address control variables. In this study, control variables are essential. If control conditions change, results become unreliable. Let us examine the key control variables. First, image capture condition, lightning, angle, distance. This must be standardized. If one group uses high quality lightning and another does not, accuracy differences may be artificial. Second, camera quality and progress. Pre-processing. Different devices may produce different image resolution. Image normalization must be consistent. Third, symptom reporting consistency. If fever is self-reported in one case, but clinically measured in another, data reliability decreases. Control variable protect internal validity. Without proper control, we cannot confidently say that improved accuracy is due to multi-symptom integration. Remember this extended model, outcome equal independent variables plus controls and noise. If controls are unstable, noise increases. Scientific research requires minimizing noise to isolate true effect. That is how we ensure fairness and reproducibility. This is the end of our class, and see you next time.